Hey everybody, Dr. A here, and in this video we're going to be exploring an example of evaluating a position vector and a unit vector. So let's go ahead and get started.
In this example, we're asked to determine the position vector from a point B to point A, then to compute its length. After that, we're asked to compute the unit vector that defines that distance from the point B to point A. So to get started, let's draw out our scenario. And again, this is all given information. I just like to draw this with you, and you draw it along with me so we can practice drawing our figures. This will be a 3D type problem. So as I've stated many times before, I like drawing my y-axis first, and then I'm going to have an x-axis coming off here, and I'm going to go ahead and show a little negative portion of my y-axis. So here's my origin, and then here is my z-axis right here. Okay, so the first thing we're gonna draw is point A. All right, so point A is gonna be about over here. This is point A, and I'm gonna go ahead and give you the coordinates of point A. So the coordinates of point A right here is going to be a 4-foot distance, and then we're gonna have a coordinate that is, oh, I'm sorry, back up a little bit. Go ahead and project this down. Here we go. 4-foot distance here, 4 feet. And then it's going to have a height in the z direction of 2 feet. So this is 2 feet here. And again, along the x-axis, it's a distance of 4 feet. And along the y direction, I'm trying to draw this as best as I can, so bear with me. There we go. And then along the y direction over here, we're going to have a distance of 1 foot. All right. So again, point A is this point that's in an octant where we have a negative y direction. So this 1 foot dimension right here, notice it's actually negative. In fact, if you want, you could put a negative right there to indicate it's along the negative y-axis. So that's point A. Now, point B. What about point B? We're going to put point B down here. Point B, okay? And point B is actually going to be in a negative region as well, somewhere like in the below the origin, in the negative z direction. All right. So again, trying to draw this as best as we can. We're going to come up here and project it to the XY plane. And right here is going to be a distance of 5 feet along the positive y-axis, okay? And then the distance in the x direction right here is going to be 1 foot. So on the x-axis, this is positive 1 foot. And then the z direction here, that's going down by an amount negative 1.5 feet, okay? So I know this isn't my best artwork, but this is what we're looking at. So just to point out, this point right here is kind of like the shadow of point A on the XY plane. This point right here is like the shadow of point B in the XY plane, where point B itself is actually in the negative Z direction, and point A itself is upwards in the positive Z direction, but in the negative Y direction, okay? So the position vector we want it from point B to point A. So the position vector that we're really interested in is this position vector right here. Notice we said from point B to point A. So the arrowhead is at point A in this case. All right. So that's our figure. Again, you want to practice drawing this the best you can. And let's go ahead and start looking at this. So if we say solution here, solution, notice that we are given coordinates, right? So what are the coordinates that we're given? So let's look at point A first. The coordinates of point A, x sub A, comma, y sub A, comma, z sub A, are the following. In the x direction, we are 4 feet in the positive x direction. We are negative 1 foot in the y direction, so that's in the negative y direction. And then we are a positive 2 feet in the z direction. So again, that's where we are with point A. What about point B? So we have x sub B, y sub B, z sub B. What are those coordinates? Well, the x coordinate of point B, again, point B along the x-axis, right, is 1 foot. Along the y-axis is 5 feet. And then along the z-axis, where we went down below the origin by negative 1.5 feet. So these are our coordinates. Now we can write the position vector from B to A. Remember, the problem said from B to A, from B to A. And we even drew that with our figure from B to A. And so we always say the second point minus the first point, right? So from B to A, we say coordinates of A minus coordinates of B, right? We say second point coordinates minus the first point coordinates. So we're going to say position vector R, which this is what I've drawn right here in green. This is position vector R. You could call it R sub AB if you wanted to. You could call it R sub AB. I tell you what, let's do that. And let's be color coordinating, right? So let's use green. RAB, that's from B to A. Actually, if you go from B to A, you know, you should honestly call it RBA, not RAB. But either way, we'll just call it R. I don't really like the subscripts personally on the position vectors. I avoid them, but the textbook uses them sometimes, so that's why I kind of mention them, but I normally don't like them. So if we say from B to A, then what are we going to do? We're going to say coordinates of A minus coordinates of B, 4 feet minus 1 foot, I, plus negative 1 foot minus 5 feet, J, plus 2 feet minus a negative 1.5 feet, K. All right. So you got to be careful because there's some negatives floating around here. We say coordinates of A minus coordinates of B. So there's a minus sign in each one of these terms because of the nature of subtracting the two. But remember, some of the coordinates are negative just because they're in a negative region. That's why this is a -1 and this is a -5. So just be very careful with this. When we do some rearranging, we'll get that position vector as 3I minus 6J, and then plus 3.5K, and we can put units of feet out to the right, or you could put the feet inside of the vector if you'd like. So that's our position vector. And again, technically we could call this R sub BA. I said RAB earlier, but when you label these, you want to always call the subscripts. You go the first subscript is the letter that you're coming from, and the second subscript is the letter you're going to. So technically we could call this RBA. I made a mistake a few minutes ago when I said RAB. Because we're going from B to A, you label it RBA. So again, it could lead to some mixing things up, because when you're doing the mathematical operations, you're always saying the second coordinate minus the first coordinate, which in this problem, that's why we said coordinates of A minus coordinates of B. So just be organized with it, and keep things straight in your head. I've flip-flopped things plenty of times because I made that mistake. So moving on. We got the position vector. That's it. We did this. We just did this. Compute its length. Okay, that's where we apply the Pythagorean theorem. The length of it is just its magnitude, right? Its magnitude is the length. So we're gonna say apply the Pythagorean theorem, which is essentially the distance formula, right? So 3 feet quantity squared plus negative 6 feet squared plus 3.5 feet squared. And remember that negative 6, that itself gets squared as well. So if we punch that through, we'll have 9 plus 36 plus whatever 3.5 squared is. And then we take the square root of that. So I get 7.57 feet is the magnitude of that position vector, or its actual length. So there's the next part of the question. And then the last part of this example says, compute the unit vector that defines this distance, okay? Compute the unit vector that defines this distance. So the unit vector, U, and you could call it U sub BA if you want, but that's going to be the position vector divided by its magnitude, okay? So if you take the position vector divided by its magnitude, that would be 3i minus 6j plus 3.5k, all divided by 7.57 feet. And again, the numerator carries units of feet as well. And so if you kind of package this together and you divide some values out, we would end up getting 3 divided by 7.57. So we get 0.3963i minus, again, 6 divided by 7.57. So minus 0.7926j plus, 3.5 divided by 7.57. So plus 0.4624k, and that's the unit vector that defines the distance or the position from B to A. So if you want to double check that this unit vector is correct, you can always compute the magnitude of this unit vector, and you should get a magnitude of what? Of 1. You could also compute coordinate direction angles, right? Because we know that this value right here is equal to cosine alpha. This is cosine beta. This is cosine gamma. So if you wanted coordinate direction angles for the position vector from B to A, you could get that as well. Just to keep in mind, remind yourselves what you can get out of this besides what we just calculated. So here you'd make a summary, and you would box in your answers with a straight edge for the Cartesian vector R, for its magnitude, and for this position vector.